Okay, so now we proceed to the final part of this syllabus of normal distribution, which is normal approximation. This comes as the last part of binomial distribution. So in addition to this is an addition to binomial distribution. Now, why is it that a binomial distribution can have a question that allows us to use the normal distribution? Because, see, the binomial distribution is only applicable when the data is short. On average, I would say if there are 30, the number of trials are 30. For example, I threw a dice 30 times. I'm observing 30 people's ages. I'm observing 30 people's IQs or 30 apples. That's something the binomial distribution can deal with, and plus you can manually get to the answer. But when you observe data that is greater than that, what happens is the mathematicians observed that again a bell curve had begun to form, and whenever that bell curve is observed, what does it mean? That it is now a normal distribution. So we saw, okay, so what if when we are dealing with something along the lines of a binomial distribution and there is too much data? What if to make our lives easier, we converted it into normal distribution and did it and found our probabilities way easier, and that way we can observe more data, right? So, and because are there more reasons? The benefits, let's talk about the benefits as well. The benefit is actually just one thing, which is to save your effort and time. That is all. Because binomial distribution with a lot of data will require too much effort to get to the answer, too much additions of different equations. While in the normal distribution, you can directly get to the answer, right? So it will be much easier. And hence we do this conversion. So what do we need? Let's do this question, but let's look at the steps first. First step is to do the conversion. Okay, so how do we do the conversion? Very simple. How do we represent a binomial distribution? Binomial distribution, bracket, number of trials, n, and the favorable probability, as in the 0.05 is the probability for Easea to win this battle. So that would be my favorable probability. So it be represented by P, and that is it. I know X belongs to a binomial distribution uh, with number of trials n and probability P, favorable probability P. Okay, then we say that this is being converted. One squiggly equals to and one straight equals to. So this X belongs to a binomial distribution, but is now being converted to a normal distribution, which, as we know, the mean and the variance. But in binomial, when we're doing this conversion, converting from binomial to normal, we need to find the mean and we need to find the variance. There are very simple formulas that we have already studied in binomial distribution, which is to find the mean from your binomial formula is to multiply n with p. Multiply these two together and you get the mean. Comma, how do we get the variance? We multiply n p q. Now what is q? Q equals to 1 minus p. That is q. What does that mean? It means Q is actually the unfavorable probability. That means 1 minus 0.05 is 0.95. So 0.95 is the probability that Easea will lose this battle, right? So to find the mean from the binomial distribution, because the data is arranged in the binomial terms, so we need that mean. How do we get that mean? N into P. How do we get that variance? NPQ. When you have these two, so to write it more precisely, actually no, this is good enough. Instead of mean, actually now I'll erase it for you to make your lives easier. Instead of the mean, I'm just gonna write. Uh, Actually, let's remove that. Please note this down after you pause the video or something if you can. There we go. Remove that, all that, all that. So now that you know what that means, so the mean is going to be NP and the variance is going to be NPQ. And that is the notation for your conversion. Now, before you start solving, you need to understand that there are some conditions that need to be fulfilled for a binomial distribution to be able to be converted into a normal distribution. Because not all data, the data might not be enough for a bell curve to form, right? The data might not be enough for the standard normal distribution to take care of it, right? So there are certain conditions that need to be met. Not all data can be normally distributed, right? So some conditions are conditions that need to be met, and I would urge you to show this in your exam as well. The first thing you're going to do before you show this notation, you're going to write the condition n into p. You're going to multiply this, and this should be greater than 5. If this is met, you can proceed. But there is one more condition before you proceed. That is, you you multiplied n and q, and that must also be greater than 5. I think there was a question of this asking for the conditions in 2022. I don't remember precisely, but it was around 2022 that they asked for the conditions that you need before converting binomial to normal. So these are the two conditions that will be enough. Another not so important one is that n is the number of trials are greater than equal to, not greater than equal to, but greater than 30. But this is where not very relevant. You can write it, you cannot write it, it's your choice, right? Anyhow, so these are the two conditions that need to be met to fulfill this, to make this conversion. So the first step, make sure the conditions are met, then proceed with the notation. Then, now let's start with the question and move to the second step. So the question says 120 students. So how many students are being observed? 120. That's my number of trials, number of candidates. Whether they have passed the exam or not. 20% of the students passed the exam. Okay. So favorable is 20%. In probability terms, divide that by 100, remove percentage, that's going to turn into 0.2. So that is my favorable probability. And use a suitable. Now this is your keyword. Until and unless the examiner uses this phrase, let me change colors, use a suitable approximation, you are not going to convert into a binomial distribution. Okay, or you are not going to convert this binomial distribution. So now that we know we're going to convert into normal, that means do the conversion, right? To find the probability that more than 50. Okay, so what's the variable looking like? The probability that more than, okay, so x, that is your data store, as in the number of people that passed, is greater than 50, right? Have students have passed the exam. Okay, so now we have analyzed the question. The first step was converting, so let's do the conversion. Let's do the first step side by side. So let's just remove this for a second. Like that. There you go. Now do the conversion. So x had belonged to a binomial distribution with trials 120 and probability of 0.2, but now is being converted into a normal distribution with the mean 120 into 0.2. That is, I'll calculate that later, not a problem. And the variance 120 into 0.2 into q is 1 minus 0.2. So 1 minus 0.2 will be 0.8 into 0.8. And that is your conversion. Now that we've converted, that's our first step. What is the second step? The second step is even simpler. It is that you need to understand that when we were dealing with binomial distribution, the variable we were calculating, that more than 50 students, this variable, this number representing these students, 50 students, is a discrete random variable, as in the number of students. This data we are studying is a discrete random variable. It's in whole numbers. But if you remind yourself, I told you normal distribution works on continuous data. It is in real numbers, right? So we need to apply a certain correction that will allow this variable to be read in the normal distribution table or the Z table. So how do we do that? Well, we use a method called continuity correction. So we're going to learn to apply that continuity correction. There we go. So how do we make the equation? First, make the equation that satisfies your question. That is, more than 50 students have passed. So find the probability that a number of students are greater than 50 that have passed. But this is a discrete random variable. What do we need? We need a continuous variable. So let's do some practice with this. So now let's just do some practice sums of continuity correction, understand the method and get the hang of it. So now continuity correction relies on only two things. That is going to be your inequality and the questions you're going to ask on it, and the radius. Now what is the radius? The radius is equal to 0.5. This is something that you will understand when you practice. When you with me, these 5 parts are made for you, and you're going to make sense of it. So, but this is a fixed value. You need to keep that in mind. Bearing that in mind, let's now move to the inequality. So the first thing we're going to do is ask this discrete random variable a question. That is, variable, what is the first value that you accept? So this variable is now going to look to the inequality, and the inequality is going to tell it you only accept values that are either less than or equal to 10. So what is the first value you're going to accept variable? The variable is going to tell you, okay, so I only accept values that are less than or equal to 10. So which is the first value? It's going to be 10, because less than equal to 10, right? So the first value is going to be 10 itself. Now you're going to use the radius of 0.5. Now what does the radius do? Radius in a circle is what? Distance is same from the center to the circumference, right? So what are we going to do? We're going to move up and down using the radius. So moving up is addition, moving down is subtraction. You're going to add 0.5 to it, and that's going to turn into 10.5. You're going to subtract 10.5, you're going to subtract 0.5, that's going to turn into 9.5, right? So now we have used the radius to get two more values. We have basically introduced continuous data. We've turned 10 into two continuous values, which are real values, right? Because at the moment, x only accepts discrete values, which are whole numbers, right? But we need to change it in such a way that its meaning does not change, but now it also accepts real values, which are continuous. So now the variable will change into continuous. That's why it's called continuity correction, right? So make your arrow. Now that we have formed the data, we have understood the questions and in the inequality. Now let's move to the continuous side of the equation. Okay, so let's copy the same thing, probability of x, which is now a continuous variable. Now, do not copy the exact inequality, only the basic one. Less than equal to, okay, so it means less than, na? So only copy less than. Before you add the equals to sign to it, you need to first understand the value itself. So only take the basic inequality. Okay, if it's less than equal to, take less than. If it is less than, stick to less than. If it is greater than equal to, stick with greater than. We have to change it later on, right? So x is less than 10. No, we have to take a real value. So either one of these will be accepted. But sir, which one of these do I take? That is the right question. Okay, so we can clearly not take 10. We can either take 10.5 or we either take 9.5. Now again, which is something that will fulfill the meaning and maintain the meaning of the discrete variable. Very simple. We're going to ask the inequality, okay, inequality, what do you mean when you say that it only accepts less than equal to 10? It says that I'm not going to say it's the same thing again. It basically says that all the data will be 10 or less than 10, 9, 8, 7, 6. Okay, so that means either value I take must round down to 10. Okay, it cannot go any other direction. It cannot go to 8. The first value must be 10 and it must round down. Why? Because the inequality says that I only look to values that are 10 and less than it, below it. So that shows me that the real value must be satisfy this condition that 10 that the real value rounds down, lessens to 10 itself. So tell me, if I round down 10.5, what is it going to turn into? It's going to turn into 10. And what will I get if I round 9.5 down? What is it going to round down to? It's going to round down to 9. So which of these do I accept? I accept this one. And it is generated from which real value? It is generated from this real value. So now I know I need to put 10.5 here. Okay. Now, sir, you were talking about something about the inequality. Okay, so now you decide if the inequality is going to remain less than equal to, or is it going to change to less than? Well, that is a simple question. You're going to ask 10.5. Okay, 10.5. Do you, for following the rules of rounding off to the nearest whole number? If I round off 10.5 to the nearest whole number, what is it going to turn into? It's going to turn into 11, not 10. The first value we were accepting in the discrete variable was 10, not 11, right? But if in the continuous side I've taken 10.5 and I say less than equal to, that means 10.5 itself is accepted. But does 10.5 round into a whole number that is 10? It does not. 10.5 rounds to a whole number that is 11, which is unacceptable. Which is why, my friends, I said it must lessen to 10. That means it lessens everything below 10.5. What's the rule, by the way, of rounding off? Uh, if it is 5 and above 5, it rounds up to the next number, and if it is less than 5, it rounds to the number below, right? 95 is going to round up to 100, but 94.9 even is going to round up to 90, right? So when I say less than, I say that every value beneath 10.5 is going to be accepted by this value. So which is why I was focusing on the value that it must lessen to 10, right? It must round down to 10. So when I put this value and I talk to the inequality, then that inequality will make sure that this value is not itself is not accepted, because we know this will round up to a whole number that is 11, which is not accepted by our discrete value. Instead, we accept 10. So does this round up in, so if I take every value that is less than 10.5, does that round up to round down to 10? Yes, it does. But that means our boundary that we've set satisfies our discrete value. It maintains the meaning. And hence, now finally, we have converted our data into continuous data. So I hope that was not too complicated. Now, when we get into the flow of those difficult things in these four parts, it's gonna make sense. Here we go. So, let's identify the first value x will accept. X is less than 10, right? So inequality, which is the first value x will accept? Okay, so anything less than 10, which is the first whole number value that is less than 10? It is 9. So the first value, this discrete value, this discrete variable will accept will be 9. Okay, so now use the radius to get to 9.5. That is 1.5 above, and zero point 0.5 below will be 8.5. Okay, so now we come to the continuous side, right? Probability x, use less than. Now, which of these value do I put here? Okay, so let's ask the inequality again. Okay, so now inequality, which value should I take? So the inequality will tell you I take all values that are less than 10. That means they must be below 10. So, okay, so the whole number's value is 9. So that means the two real values I have assumed, I have introduced, one of them must round down, lessen to 9, right? So because everything below 10 is being accepted, not equals to this time. So everything below. So the first value below is 9. So the real values that will be introduced must round down to 9. So okay, so does 8.5 round down to 9? It absolutely does not. It rounds up to 8.5 would round up. Actually, it will round up to 9. But if I round it down, what is it going to round down to? It's going to round down to 8. So if I talk to 9.5 round ups to 10. But do I want that? What is my wording? My equation tells me, the inequality tells me that it has to lessen to 9. So does 8.5 lessen to 9? It does not. 8.5 will lessen to 8. But if I talk about 9.5, does 9.5 lessen to 9? Yes, it does. So lessen to 9. So I will, and this 9 is again formed by which real value? 9.5. So you're going to take 9.5 here. Now talk to the variable. So does 9.5 itself round down to 9? It does not. So it's going to remain less than, right? Less than remains less than. Because every value beneath 9.5 rounds to a whole number that is 9. And that is exactly the value that my discrete variable was accepting, right? So now let's quickly do this one. Probability of x greater than equal to. Now the meaning is going to change because the inequality has changed. Those were the less than cases. These are the greater than cases, right? So greater than, okay, so just write greater than there. Now talk about the value. X is greater than equal to 10. So the first value is going to be 10. Use your radius to get to 10.5 and 9.5. Now, what do you accept? Everything that is itself 10 and above it. So that means now the rounding will not go beneath, because now we're moving up. We have to move up. Okay. So the first value that it accepts must be 10. And if I introduce real values, they must round up to 10 itself, right? So if I talk about 10.5, does 10.5 round up to 10? It does not. It rounds up to 11. Does 9.5 round up to 10? Yes, rounds up. It rounds up to 10. And this 10 was generated from which real value? 9.5. So I'm gonna write 9.5 over here. Easy does it. Now tell me, does 9.5 itself round up to 10? Yes, it does. So now it's going to be greater than equal to, because 9.5 itself and 9.6, 9.55, 9.5.5, 9.51, 9.52, everything will round up to 10. And 9.5 itself will also round up to 10. So it's going to be greater than equal to. Hope that made sense. Here we go. Final part. Probability x is greater than. So just write greater than at the moment. Now talk to the inequality. Inequality, what's the first value that x is accepting? It will be, sir, anything above 10, not 10 this time, everything above 10. Now what is the first whole number value that is above 10? Well, sir, it is 11. Okay, so now use your radius to get to 11.5, and below is 10.5. So inequality, which value do I accept? Inequality is going to say, okay, all the values that the discrete value was taking, that the discrete variable was taking, were above 10, right? So you need to, so the inequality is telling me, so Isa, you need to select, oh my God, is that a crow? Crow, please leave, man. I'm trying to teach you. We're learning. Anyway, so so inequality is telling me that Isa, you need to select a value that must round up, it must increase, because this equation only talks about something that increases, not the questions that you were doing above. In those questions, something was decreasing, all the values were decreasing. So that's why the rounding was beneath. But this time, Isa, the rounding must be above. So you must select a real value that rounds up to 11. Okay, so the first value I was accepting was 11. So the real values that I've introduced, one of these must round up to 11. 10.5 does that. 11.5 would round up to 12. That is unacceptable. So 11 is generated from 10.5, the real value called 10.5. So you're going to write 10.5 here. Now, does 10.5 itself increase to 11? Yes, it does. So it is equal to. Right, that is how simple it is. In the beginning, imagine how hard it would do, how difficult it sounded, right? But now you've gotten the hang of it, and now you can do it. I'm pretty sure you can. I hope you can. Now this is a special case. I have not seen this in the exam, but it would be better to get it over with. Probability in a case when the variable is only accepting 10. So to convert it into a continuous variable, you're gonna do both bounds. That means you're gonna take care of the upper bound. You're gonna take care of the lower bound. That means x above it would be moved from the radius, so 10.5, and below it would be 9.5. So 9.5, and write 10.5 as well. Take both sides of the radius, right? And I'm going to do something special here. I'm going to write this. Why did I do that? Because 9.5 would increase, because x is greater than equal to 9.5. 9.5 itself would increase to 10. And does that satisfy this variable? Yes, it does. It maintains its meaning, right? So there's going to be equals to there. But why is there a equals to not here? Because 10.5 does not increase to, you guessed it, it does not increase to 10. So I hope the continuity correction method was clear to you guys. This is the way I learned it, and this is my own method of going about it. It's a little difficult, I would agree, but I think it's the easiest one. It is the least complicated one, I would say. That's how it made sense to me. So now moving back to our question, here we go. Continuity correction to our variable here. So probability is x is greater than 50. Okay. So this is a discrete random variable, right? So now I'm gonna convert it into a into a continuous variable. Okay. So probability x, inequality is less, so stick with less. Sorry, inequality is greater, so stick with greater. What the hell? Greater than, there we go. Greater than. Now let's talk about this value 50. Okay, so ask the inequality. What is the first value x is going to accept? X says I'm gonna all the values that are greater than 50. So what is the first value you accept? It's gonna be 51. That's the nearest, that is the first whole number value, right? All the values must be greater than 50. So the first whole number value will be 51. Now use your radius. You get to 51.5 and you get to 50.5. Okay, now inequality, which of these real values should I take? Well, Isa, you must take a real value that rounds up to 51. Why should it round up, Isa? Because I only accept the variable x only accepts values that are greater than that, increase from 50. They are never 50 itself, but they increase from 50 and they go to 51, 52, 53. Now, since you're unlocking the real values as well, you must choose a real number that rounds up to 51. Okay, so okay, inequality, I get it. So 51.5, does this round up to 51? It does not. 50.5, do you round up to 51? Yes, you do. So it is generated from this value. So 50.5 goes there. Now, since it was increased, 50.5 itself, do you increase to 51? Yes, you do. So greater than equal to. We've done the continuity correction, right? So much easier now that we've gotten the hang of it. Do some practice if you want on your own. So the first step was what? To make sure these conditions are being met. Conditions are being met. So now you can do the conversion. This is the notation. This is how you do the conversion. Oh, where's the bracket go there? Into 0.8. I might have erased it by mistake. Anyways. So now that we've done the conversion, we have found the new variable. Now what do? We do nothing. We now solve normally. The third part of this question is to solve like normal distribution. Okay, distribution, blah blah blah. Okay, so now how if I give, now this is just a normal question, right? It is normal, x belongs to a normal distribution with mean is 120 into 0.2. Actually, let me get that answer. Give me a second. So x belongs to a normal distribution with mean 24, variance 19.2, and you need to give the probability x is greater than or equal to 50.5. Now, don't you already know how to solve this? I mean, come on. This is, by the way, non-ideal data, of course. You already know. What's the first step? We standardize it. Standardize it. The variable is now going to turn into z. So z is greater than or equal to 50.5 minus the mean, which is 24, divided by 19.2 under root. Why? Because this is the variance, not the standard deviation. Right? Standard deviation is under root the variance. Now that we have done this standardization, now let's look into the probability. By the way, let me calculate this for you. So 50.5 is going to be 50.5 minus 24. Okay, that is 26.5 divided by root of 19.2. There we go. So that is 6.04. Okay, so probability z is greater than or equal to 6.04. Now I told you, you round this to 3 decimal places. So it is going to turn into 8. 7 again. It returns into 8. Okay. So that is out of the way. Now we have gotten the z value. Now we imagine the normal distribution curve. 0 is going to be here. Here is going to be 6.0. Oh, good heavens. That is it. I made a very I have not made a good question. This value would not exist. So clearly this data was terrible. I took a random question, random data. How do we fix that? Actually, I can fix that. Wait, let's turn this into 40%. 40%. Okay, so now the question's turned into a better question that would actually fit into your Z table. Anyways, now put the answer and you get 0.466. There you go. 0.46 is going to be a little ahead of 0.466. We need all the area that is greater than 0.46. So how do we calculate that? We take the total area, subtract that from all the area that is below 0.466. So phi of 0.466. What does phi of 0.466 mean? Everything that is less than 0.466. And if we subtract that from the total, what are we left with? Everything that is greater. So please calculate this value, read this from the Z table, and give me your answers in the comments if you can, but this is going to be good enough. So that is your final answer. You already know how to read the Z table, you already know how to do that. Let's do a small review. So before we move to the past papers, let's just do a quick review here of approximation. First step is make sure the conditions meet. NP is greater than 5, NQ is greater than 5. Okay. Now then use the notation of conversion to you convert your binomial to a normal distribution. As you've seen, NP is the mean, NPQ is the variance. Right? You do the conversion. That's the first step. Then you make sure that the variable you are using is not discrete anymore. It is a continuous variable. How do we do that? We use continuity correction. We already know how to use it, right? Then the last and final step is to solve like normal distribution. As in, we know the mean, we know the variance, then we know the variable, we know the value, we standardize it, we get the answer, as we imagine it on our normal curve, and then we get our equation. We read it from the Z table and get our answer, right? That is the step. It is going to go way faster than it did right now, but this is it. That's done. Congratulations, you're just done with normal distribution. Be genuinely proud of it with yourself, because this is great work. So now I'm just gonna make sure I'm gonna try to compile the question types, different questions that we've seen in the past papers, and maybe do some videos uh, on like a marathon type thing, Zenomatics type stuff. I'm gonna copy that stuff, to do as many questions and exhaust this whole syllabus. Right? I hope it helped you out. Hope it made sense. The logics made sense. and it was worth it.